start for today. And signing the sheet that's here or passed around. If you come up, you can pass around. And I'd like to add that yesterday, I maybe did not quite say this clearly, that you do not require any neurobiology and biology background. This is a course for physics students, but you can learn them here. So try not to think that because you don't have biology background, you will not understand. Yeah. Secondly, I like to point out that if you think that you come here, you learn all the physics, you just want to find a problem, use your physics skill to solve it, yes, you can. However, that's doing applied physics. You can do more if you treat this as a fundamental physics problem to study the brain. Now, what do I mean by fundamental physics problem? Actually, that means a fundamental scientific and philosophical problem. That means you have to formulate the question yourself and ask the question yourself. And this is unfortunate that often our curriculum in physics education is so full that we usually have the problem defined for us by Einstein and by Isaac Newton and Dirac and so on and so forth. And we just learn the techniques to solve the problem. And we do not have a chance to ask the problem as many chances as they say 1900. Yeah? When 1900, we don't know what's going on. You have to say, what is the problem? But in fact, doing science, one of the most difficult things and the most fun and interesting thing is to ask, what is the problem? And you can say that even if we miss the time to be born in quantum mechanics, we are in time for the problem of the brain. And so if we do that, we'll have more fun. But you can just kind of put yourself in a position to say, I just want to do only applied physics problem, not a problem, okay? So just say, where do I want to put it and try to enjoy. Okay, this is what I want to say. So yesterday, we had started with, where is it? Yeah, yesterday I talked about, we are going to talk, first start with, let me also put it into, first we start with data, because any science has to start with data, otherwise become philosophical, right? So we look at the data, a little bit of introduction. From today on, it will be trying to use this approach of understanding the data by theory, okay? And the first 3 lectures, today, Wednesday, and Thursday, it will be understanding by kind of like classical signal processing theory. And then Friday on, we are going to have very fundamentally different theory. And again, you will find in these, what is it, the problem? How do you formulate the problem, whether it's classical ones or modern ones? The modern ones can be even very fundamentally a bit upsetting because they are very unfamiliar, but the brain is an unfamiliar, interesting organ, so therefore we have to deal with it. And then on Thursday, we are going to talk about things like next week's Thursday. We talk about the history of vision science. And you say, where are the theories? How many theories are successful? Why are there so few theories? Okay, and then therefore, the new generation, what is on your shoulders and things like that. Why is this theory failing and why is so many heresies going around? Yeah, are they really theories or they're pre-Newton era stuff or something like that? So by having all these raw materials in the first few lectures, hopefully we will have enough to debate and discuss, okay? So for example, you say, why am I teaching these theories and not other theories? Because there are very few theories. So the choice that I'm take to teach these theories is because these theories are falsifiable. And by definition, falsifiable theories are scientific, and non-falsifiable theories are not scientific. So I choose only the falsifiable theory, and actually all of them, except maybe for one. Yesterday we talked about Maxwell had a fundamental theory established for trichromacy, 3 color mechanisms. That was a beautiful classical theory. Of course, you can say you expect no less from the great Maxwell, yeah? And so I will briefly mention that next Thursday when I talk about what are the theory. And then the rest of the theory, in fact, we all talk in this course. So today, let's start with our first one, okay? So we're going to talk about efficient coding theory, and you will find in the online course these 6 chapters, which can be supplementary. If some bit I go too fast, you can look up in these 6 chapters. And it will be connected with the data I showed you yesterday. And so if you did not quite get the data today, you have another chance now to put it in the context of what is the question, what is the theory, and so on, yeah? So here is the motivation. The motivation is, you know, in biology, you see these all kinds of different things. You know, cat does this way, bird does that way. You know, retinal ganglion cells have center-surround receptor field. And these receptor fields are not even fixed. They change in a matter of minutes. When you go from the ocean to indoors, they change. Okay, they're very adaptive. They change when you evolve from monkeys to humans, you evolve from fish to cats, yeah? And why should the contrast sensitivity function going in that way? Why is this particular way? So there's lots of why questions. And these are really the questions only answerable by some principles, yeah? Not how and what. Now, how and what could be an engineering question, could be something else. The why is where a theory, fundamental understanding can come up from. So why are the color selective V1 neurons less sensitive to motion signal? Okay, you can have something, if something is moving, then you see the color, you actually don't see it's moving. It's very interesting. How can we predict some of these things? And so many whys, and some of these data we actually talked about yesterday. So the question is, can we derive all of them from one single theory? Okay? One single theory and derive all of these as just explicit examples. Just like if you have Newton's law, you can apply it to extraterrestrial as well as on Earth, yeah? You can apply it to a dog running, a train going, a rocket throwing, all these things, okay? So what is the theory? So about half a century ago, people tried to understand it as all of these are just sensory signal coming in. You want to reformat it by a particular goal. So the idea is raw input comes in, you encode it, you transform it into some kind of an output. And then what is this transformed for? That's the theory, okay? And in the process, you have some noise because you are dealing with a physical system. Every time you do something, you add a little noise. This is not avoidable. But your external signal is also noisy. Just imagine you look at television or you look at, you know, your eyes, you know, this crowding when the image comes in, okay? And so therefore, the external noise that comes in and the internal noise that comes with the encoding will give you the total noise at the output. And therefore, you can measure how much information you gain about your real input you want through this output. Then you send to the CPU to process. Okay? And you can measure this information as something called mutual information. I will elaborate. Yes?
Yes. Sorry, regarding to yesterday, when we have this filter,
yeah.
we begin with the ganglion cell and
yeah.
then the V1 cell.
Yeah.
The part before the ganglion cell, the eye, does
yeah.
not act as a filter.
Yeah, it is. You can say everything is K. Okay? The eye, the lens is a transform of the light into your neural signal. Okay? So you can say S is actually the light. Okay? Then anything you do with it until the ganglion cell output or some kind of output is a transformation you're trying to achieve. Okay? And your transformation is done by a physical system, which is your brain, which has limited power, limited number of neurons, and limited time. So it's a constrained problem under constraint of limited resources. For instance, the neuron cannot fire more than how many spikes per second, and how much power it can do to do that, or so on. And therefore, you have to optimize what is the transformation you could do given these constraints, but still trying to extract as much information as possible. Okay, and then this is the principle. This is, so what does that mean? You want to transform such that this is a much more efficient representation of the information you want, but your raw input is not an efficient representation. Now let me dive into details. Okay, dive into detail. Give you some example. What do you mean by efficient and not efficient? And that's why this theory is called efficient coding theory, because you want to do the transform to make the coding more efficient before. So for example, when you send an email to your friend, if the email is too big, you compress it before you send. Otherwise, your friend will be upset. This compression is a transformation. And when your friend receives it, you can uncompress and see the original email. Yeah? So you can say compression is an efficient representation of the signal once you compress it. Before you compress it, you can say this is before you compress it, this is after you compress it. Okay? But compression only works well when there's not enough noise. If it's too much noise when you compress, you get all rubbish out. Yeah? So sometimes efficiency, when there's noise, it's in another form. So let's see what happens. Okay? So therefore, we will have situations with high noise and low noise. So for example, in this room, it's actually quite high noise, especially if we turn off the light, because the light level is not as high as if we go outdoors. Okay? And so in fact, your retinal ganglion cell has a different receptive field when you sit here, and if you go out, it will change within 1 minute. Really, really fast. You may not even realize it changed, because the central brain is getting lots of invariant things out of it. Okay? So the formulation was originally actually proposed by a biologist who regrets that he did not learn enough mathematics. Very interesting. It's a little bit like Charles Darwin can formulate a theory of evolution without much mathematics, and he did get hindered by not knowing mathematics. So therefore, he just said in words, he said, one of the goals of early visual processing is to encode a visual input in an efficient form. Okay, taking advantage of statistical regularities, because things are not random. The input is not random. There's regularities. And so the goal is such that the maximum amount of information can be extracted and transmitted under the constraints of limited neural resources. Now let's put in a mathematical form. It was not originally formulated mathematically, so this was 1950s and 60s. This person also played a big role. And in the 1980s and 90s, people start to put it in more mathematical form. And this way, you can derive precise predictions. Otherwise, it's a bit like a hand waving, yeah? And only when you have precise predictions derived, you see its power of applications in lots of areas. Otherwise, it's only one specific example, yeah? And then you can be also tested against data to see whether it's correct. So, what is the mathematics? Okay, and then once you have the theory, you can compare with data, say whether the theory is right, what is wrong, or maybe is theory only partly right in this domain, but not right in another domain. So it will have a restricted domain, and then a new theory has to come and replace it. Okay, so even though Newton's law is not 100% correct, it's applicable in most domains of everyday life, but not applicable somewhere else, and things like that, yeah? Okay. So the idea, again, is you have an input signal with a noise. So the signal is S, noise is N, and the total input before you even hit your retina, you call it S prime. Okay? And then your retina does something to it, transformation by receptive field. The lens, you have a cardiac, your lens was smeared a little bit, or you have, astigmas, all these kind of things. And then after the transformation, you have this transform, of course, is also applied to the input noise, unfortunately, because it could not tell which one is signal, what is noise. And add on top of it this encoding noise. So the total noise is this whole thing. Okay? And the signal is only that. So this is written as something people who in machine learning or optimization or operation research would be comfortable with is written as an objective function in which you want to minimize this quantity. And this quantity is minimized when you have a large amount of information extracted about your signal while constraining your cost. So that was a particular written formulation, so let's expand it. What is this mutual information? And fortunately, this is done in 1948. Shannon and Weaver have this information theory, and they define beautifully. So this is something you're comfortable with. It is actually the entropy in your signal, minus the conditional entropy once you know the output. Because once you know the output, you constrain on what is your signal. So originally, the signal is distributed in the whole range. So after you know this, the signal is distributed in a certain, this is just got uncertainty, right? Entropy is how uncertain you are about your signal. Originally, the uncertainty is very big. Once you know your output O, you get, there's less uncertainty left. And the difference is the extracted information. Okay? So of course, let's expand it. The entropy is written in this way. So the first term is this entropy. Okay? The second term is exactly the same entropy, except you use conditional probability. And this is the original probability. Okay? So therefore, you say, what's the difference? Then what is the neural cost? The neural cost often is written as the channel capacity. So therefore, let's say at the output, you have different components. O is a vector with different components, OI. Each of them will occupy some kind of an entropy, have some kind of entropy. So that each of them is actually the cost of your sending the data, okay? You send 1 megabytes of data. It's in terms of each of these components sending out to your friends through email, and how much it would cost your channel capacity to send it, yeah? And this is one way of talking about the cost, because let's say you have a broadband internet or narrowband internet. If you have broadband internet, you have a bigger amount of cost to spend. Sometimes people also simplify it as, this is not simplify, it's actually a very good formulation, as a dynamic range. That means the average power that you use to send all these signals. Yeah? You say, I have 1 gigabyte per second to send it, or only 10 bytes per second to send it. It depends on how thick is the channel you have. We have an optic nerve go all the way there. That's a physical channel. Yeah? Okay, so that's the cost. Okay, so this is again this is called the channel capacity or the power capacity. You have every time you do something, you have to fire ATP. This is the energy cost. And our brain uses a lot of energy just for firing. Okay. It costs a neuron to fire more. Okay, this is actually people have already measured how much. I do not remember exactly what is the number, but firing is one of the most expensive things. But even if you're not firing, you just sit there, your resting state brain is costing a lot as well, yeah? And so if you do, on top of it, thinking about a very string theory problem, it only costs a few % more. So just to maintain a brain alive actually costs quite a lot, okay? Yeah, mm-hmm. Yeah, the conditional, yeah.
I didn't understand what is it conditioned with.
Okay, so for example, let's say you have your input signal that can go from 10 possible values, okay? Let's say this S could be equal to 0, 1, 2, 3, 4, 5, 6, 7, and 9. 10 possible values. And your output says, let's say your output says, let me give you an example, okay? Let's say your output says S is equal to 5. But there's a noise. Maybe S is equal to 5. Maybe S equal to 4, because there's noise added on to top of it. So therefore, originally, the probability distribution may be a flat probability distribution with 10 possible values, let's say a flat, or some other distribution. Then once you know O is equal to 5, you say, oh, S is equal to 5. Well, actually, S could be 5, could be 4, could be 6. So the conditional probability is narrower. So this is the conditional probability. The conditional that you already know what O is, then what could be the S? Originally, S is 10 possible values. Now you only have 3 possible values. That's the conditional probability. Yeah? We'll give you some more examples later, hopefully. But best you actually go back to this online course where every little thing have a 5-minute video to explain all the concepts. Okay? Very good. So therefore, you can understand that the mutual information between two terms is actually a symmetric term, okay? Whether it's mutual information about O about S or S about O is actually exactly the same. Because the entropy minus the conditional entropy is the same if you write it the other way around. And this is also in these videos that you can look, 5 minutes video, okay? And turns out this is an equality. So therefore, it's the entropy of each of these things minus the joint entropy. Okay? So for example, when you receive an image, the image usually, all these, yesterday you were having the image downloaded, and you do process on it, and usually, typically, each image pixel have 256 possible values, right? 0, 1, 2, 3, 4, all the way to 255, integer values. Okay? So this 256 integer value costs you 8 bits of uncertainty. Okay? So therefore, you can say this PS is a probability distribution all the way from 0, 1, 2, 3, 4, all the way to 255, or possible, this is your PS probability distribution. And then if you write its entropy is equals to minus S, probability of your possible S, your signal, and log 2 PS. And then you find that if it's evenly distributed, flat distribution, everybody, then this is exactly 8 bits. Okay, 8 bits is 1 byte of information. Okay? So you can say that maybe you're trying to transmit 1 pixel of information, 8 bits. And this is another, but let's say you also represent it in your output cost as 8 bits. Of course, at the output, you can say I only represent it as 1 bit, black or white, dark or bright. Okay, you can quantize it into only 1 bit, which is just 2 values. Okay, so therefore you can say this 8 bits actually comes from equals to log of possible values you have. That's 8 bits, because each of this is 1 over 256 if it's even, and this is 1 over, then you will get its 8 bits. But normally, if it's not evenly distributed, it's actually less. Okay, so this is always an inequality. Okay, so let's say the joint probability distribution together is actually 10 bits. Then the mutual information is 6 bits. That means you do not get all your 256 values very clearly. You actually lost 2 bits on the way. Okay? It only transmits 8 bits, 6 bits out of 8 bits. So that means you lose 2 bits. How much is 2 bits? 2 bits is 4 different values, okay? Because 2 to the 2, because this is a log base 2, okay? 2 to the 2, 2 bits is equals to 4. So 4 different values. So that means originally you have these 256 values. Now maybe you just lump these 0 to 3 as 1 chunk, and this is another 1 chunk, and you in the end only have 64 chunks of things rather than 256 chunks of things. You just lost some details, yeah?
I don't understand why we have 205
yeah.
possibilities. Why is this not?
This is given. Let's say I assume that's the case. Yeah, sorry about this. Yeah. This is given, but you can have your natural environment giving you that the probability distribution is given by your natural environment, such as what is the distribution of your light level, what is the distribution possibly the tiger might come, probability, things like that, yeah. And this is given by your environment. And the environment for you is different from the environment of a dolphin in the ocean. And so therefore, you will have different environment, different animals, and that will give you different result, okay? So because different environment have different probabilities, this will be different and all of these different. Therefore, the possible K transform should be different. And this is the hope where you try to use this theory to get different possible neural transform in different animals, just because they have different probability.
So every species or every have a different probability of possibilities depending on the structure of his brain.
That's right. That's right. The structure of the brain is shaped by the environment. The environment gives a probability. Then, if you optimize this thing, it will give you different solutions. So you find this K for different probability, give you different solutions. Yeah. So different animal is different probability. Indoor, outdoor environment, when you go to live in the forest and live in the urban environment, is different probability. Your brain will be different.
But it is constant for human, it is a constant value for horse.
No, it's not a constant value. As I say, if you go to the forest, it will different value. Yeah. Yeah. When you dive into the ocean, it's another value because the light gets scattered in the water is very different from the light in the air. So therefore, your color vision, a fish's color vision and your color vision is different because of this water quantities. Yeah. And so then you say, oh, the same theory explains the fish to human everything. That's the goal. Yeah. Can we do it? Or maybe it can. Maybe it cannot. Okay, so let's try to see. Very good question. So, yeah.
You said we lose two bits of information, and like we are kind of coarse graining what we're
Yes, coarse graining is a way of losing information. As if you do not know whether it's this value, that value, that value. You just put them into one value. You put all these four values into one value. You are losing the details. Yeah.
so that means the entropy is increasing.
Okay, so imagine that you have this S comes in originally can have 256 values, and you make it into an O is equal to S divided by 4. Okay, and then this is only 64 values. So your O has only 64 values left. Your O can be O is equal to 1, 2, 0, 1, 2, all the way to 63. Okay? And so your O has only 64 values. So your entropy of your O is only 6 bits. Okay? The entropy of S is 8 bits. In this case, I did it without any noise, just simply, I did not add a little bit of noise. Yeah. No noise. Let's say no noise. It's just coarse-grained. That's also another way of transmission. This transmission is by, let's say your neuron just cannot afford to fire too much. Okay, your neuron can only afford to represent 64 values, not 256 values. That's one way of looking at it.
Actually,
Yeah.
what I was trying to say that, like, based on my own knowledge, entropy is like entropy and information are kind of the opposite sides of a coin. And
Yeah.
like, if you have a higher level of number of information, you have less entropy.
That's right. Before I tell you what this 256 value is, you have 8 bits of uncertainty what S is. Once I tell you S equal to 3, you have 0 uncertainty. Your entropy is 0. Yeah, so your uncertainty is 0. Originally, you have 8 bits of uncertainty. And then if I tell you O equal to 2, very good, O equal to 2, you just reduced. So O equal to 2, it will say that if O is equal to 2, then possible S is 8, 9, 10, 11. Yeah? S can only be these 4 values. Yeah? Originally, S can be any from 0, 1, 2, all the way to 155 values. So that you have a lot of uncertainty about it, and then in the end, you only have a less uncertainty about it. Okay? And so this uncertainty is H, S, given O is equal to 2. This is the conditional entropy. Yeah? And this originally, when you didn't know anything, the total entropy is 8 bits.
So the condition is
yeah, conditional knowing that what O is, you will have less uncertainty about it. Yeah, the uncertainty is only two bits. And then you can say, okay, let's continue. Very good. All of these questions help people to clarify a little bit. So you can have mutual information between an output encoded value versus a non-encoded value. So let's also practice, because let's use Gaussian approximation, a Gaussian distribution. Here I have a discrete distribution of 256 values, all evenly distributed. But in a lot of engineering or life science situation, things could be Gaussian. So let's say this is a Gaussian signal with mean 0, and noise is also a Gaussian signal distribution. And let's say your O is simply signal plus noise. Okay, that's a very easiest situation. In the discrete situation, I just have the sum, but now if it's Gaussian, you will have to do it, with a continuous integration. Okay, now every time I have a slash means conditional probability. Okay, conditional probability. So this is the probability of noise. So, yeah, the O is this probability and that probability add together. What could be the O, for example? Then you will find this is also a Gaussian distribution, and that's also, you can find a single a video on my course whose variance is equal to the variance of the signal and the variance of noise add together. Okay, so it's a zero mean Gaussian plus another zero mean Gaussian. The result is also a zero mean Gaussian, just the variance a bit higher. And then you can go on, you apply all these to calculate the mutual information. The mutual information, once you calculate it, it's just like that. Okay, it is, so in particular, so I kind of missed a step. For any Gaussian distribution, let's say the Gaussian distribution is 2 pi square root of sigma s exponential minus s squared 2 sigma s squared. For any Gaussian distribution, its entropy, you can calculate it, is roughly log 2 the Gaussian. Yeah, it's like that, plus some constant. Okay. So this is just like here. If I have 256, values, then the number of bits is log 256 values, and that's 8 bits. Okay, so this 256 now is replaced by the width of the Gaussian. 256 is the width, the span of the possible values you can have. And this is like analogous quantity, okay? So therefore, you have that. And now you can understand this term, because this is like, what is it? This is like the entropy of your output is log 2 of the sigma of your output. And the entropy of your output, given the input is already given, then it's just the entropy of your noise. And the entropy of your noise is equals to log 2 the variance, the standard deviation of noise plus C. And so therefore, their two difference is exactly this value. Okay, and people usually call this signal to noise, roughly. Okay, actually it's signal plus noise to noise, yeah? So therefore you can see the mutual information depends on your signal to noise. Yeah, so that is a concept we have. Yeah, so this is the variance of your output, and this is the variance of your noise. Okay? You can also write it out. Okay, squared, because this is equal to that squared plus that squared. So this is your signal to noise. Okay, yeah, sorry. This is your signal to noise in terms of power. Okay? Okay, now, mutual information does not have to be between output and input. It can also between two input components. So imagine you have two, it's a picture. One input component is a pixel value here. Another input component is a pixel value there. Okay, so for example, here, this pixel value is very black, almost near 0. The next pixel value is also very black, next to 0. So two nearby pixel values are very similar. Okay, almost the same. That means there's a big mutual information between them. Okay, so if I tell you this is white, the next one pixel is also white. Yeah, so you can even look at the joint probability distribution of one pixel value versus another pixel value. They are more or less all on the diagonal. Very, very similar, okay? This is called redundancy. So your natural input comes in, there's redundant input. It tells you the same information again and again. Okay, black, 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 all these pixels all black. And then white, 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 all these pixels all white, yeah? That's the inefficiency. Okay, this is the efficiency you usually compress. When you send a photo to your friend, the compression is taking away this inefficiency, okay? And so this is called information redundancy. So two neighboring pixels have value S1 and S2. Let's say if it's a binary value or it's a gray value, okay? Binary value is having only two possibilities each pixel and or 255 possibilities. And you have a joint probability that looks like that. Okay? So once you know one pixel, then you know the other pixel so much more precisely. And it's not like as if you didn't know the previous pixel. Yeah? Yeah.
So you said when you send information, you are trying to compress it.
Say it again?
You said when you send information, when you compress it.
Before you compress it.
Reducing inefficiency.
Yes, yes. When you compress the information, you reduce inefficiency. Let's say you have a 1 megabyte of coming in. And after you compress it, only takes 10 kilobyte, let's say. And this 10 kilobyte can save a lot of, saves memory space, saves your broadband channel capacity to send. It's a much more efficient way. Imagine it's the amount of money you have to pay to save it, yeah.
My question is, by reducing inefficiency, you can also add noise to the image.
You do not want to do that. So you will probably see after 1 or 2 slides, yeah? Okay, so these two pixels are very correlated. They give you almost the same information. So now let's write it out. How much is of one pixel's entropy, another pixel, and they're joined, okay? So imagine, okay, because normally you always have some information, so usually this is larger than that. So this is always larger than 0. So imagine that first pixel is 8 bits, okay? Second pixel is also 8 bits. But because they are redundant, the jointly is not 16 bits, okay? Because you're knowing the first pixel, second pixel more or less tell you the same thing, because the probability here is not evenly distributed. It's mostly along the diagonal line. And that's why it's only 11 bits. Imagine it's evenly, uniformly distributed. Then it will be 16 bits, okay? If they're completely independent. They're not redundant. Okay, let's say this 8 bits is evenly distributed from 0 to 256. And this is also, S2 is evenly distributing 0 to 256. And if they're completely independent, then this whole space will be filled with even distribution. Then it will be 16 bits. But because it's not even, it's densely packed along this near diagonal line, it's only 11 bits, okay? And so therefore, you always have this kind of you're adding individual components uncertainty together is always more than the total uncertainty when you're trying to take advantage of this redundancy, okay? So the total is always less than, and therefore the coding capacity you would use if you just send the raw information directly to the brain, you will need this much coding capacity. However, the actual amount of information you coded is much less. Just like if you have 2 bits, you need 16 bits, but the actual amount of information you coded is only 11 bits, yeah? Now, this is only look at 2 pixels. Imagine if you look at 1 million pixels. How much more information you just wasted if you send them as individual pixel, individual number. Okay, that's the inefficiency. So the actual amount of information coded is much less, and therefore you can define the redundancy you have your information by the very inefficient way of representing it versus the efficient way of representing it -1. Okay, this is the redundancy. And so therefore, natural raw signal image signals, whether it's auditory signal, visual signal, smell signal, touch signal, they are all redundant. So if I touch, okay, so this bit of touching and that bit of touching are related. I seldom touch like that, yeah? So there's a lot of, my palm is touching, so there's all redundancy. And you want to remove this redundancy. Okay, I'm gonna, here, for example, when you use this gray value images where each pixel can have 256 values, we can actually calculate. This is one of the homework I'm going to ask you to do today, yeah? So if you do it, you will also appreciate it. And more. So you can calculate, you're given an image. This is when it's this gray value. It's actually 11.31 bits, okay? However, individual pixel costs about 7.6 bits, not quite 8 bits, yeah? Remember I said 8 bits. You say, why are you saying 8 bits here and suddenly less? It's because each individual pixel's distribution is not completely uniform. If it's completely uniform, it would be 8 bits, usually slightly less. So therefore, you can calculate redundancy. This redundancy is 0.74. So 74% of things between the two pixels are redundant information. Same information, redundantly saying it again, yeah? Okay? This is when you represent as, coding capacity used if you do not compress it is 15.3 bits because you took both. And the redundancy, well, actually, sorry. This is 74 is when you represent it as 2 bits, okay? When you represent the 8 bits, gray value is actually 35%. So actually, the amount of redundancy depends on how much detail you want. The more detail you want in natural images, usually less redundant. In the coarse level, it's very redundant. So therefore, when you have only 2 bits, the redundancy is 74%. In the details, it's only 35%. Okay? Okay, maybe I like to give you something more natural. Redundancy is also in language, for example. Or anyway, let me just, let's say for n image pixel, you actually have 50 bits of information. But in fact, individual pixel add together is actually 100 bits. Then the redundancy is about 50%, yeah? Or 100%, you say, redundancy 100%. And so therefore, raw image pixel representation is inefficient. It requires 100 bits to send the information about n pixels to the brain. Shannon says that you can encode this in another form that's more efficient, but you cannot do it less than 50 bits. Okay, so if you do less, you will introduce noise. Or if you don't have a clever coding algorithm, you will also introduce noise. So this is the Shannon limit. So if we can find a particular transform that reaches Shannon limit, that would be great. But often it doesn't completely reach, but it can still do a lot, yeah? So usually people cannot reach it, but you say, well, I use an encoding algorithm to go reduce 100 bits to 80 bits. That's already much better than 100 bits. But you know that theoretical limit is you can reduce all the way to 50 bits. Okay? Yeah?
So you are basically saying that the 50-bit representation of the 100-bit image is like the most efficient way to represent.
If you can find a particular clever encoding algorithm. Usually people cannot find such a clever way to go all the way to 50 bits. Usually it's reduced. Not only clever, your hardware constraint. Let's say you are only allowed linear encoding, not nonlinear encoding. Then it will constrain lots of ways. Yeah? And so therefore, this is only theoretical limit. And sometimes to reach this theoretical limit, you have to wait for a whole hour of input before you encode it. By then, you're already eaten by the tiger. The biological animal has to decide, there's a tiger coming, I need to run. So they have a limited time as well as limited hardware, limited algorithm, limited hardware to implement this encoding transform. Yeah, good. Yeah,
Can we say that Shannon limits in information theory is like Carnot machines in thermodynamics?
You can say thermodynamics in the end is fundamentally statistical nature in the statistical mechanics. So Shannon information is also statistical based. So I would not say they're exactly the same, but statistics give you a probability. Yeah, so it's all probability-wise, because everything is expressed as entropy, and yeah. So this is a mathematical limit in the probability theory. Yeah. Okay. So let me give you something even better. Okay. You look at this sentence. It's very noisy. Okay. Some letters are deleted, but you know what I'm talking in the sentence? I'm saying I would like to invite you for dinner, right? Despite all the noise. Why? Because there's redundancy. Yeah? So when you say I, WLD, oh, must be OU. So you can, using redundancy between letters to predict what the missing letter could be. Yeah? So in language, you have this redundancy. Okay? In image, you have redundancy. And redundancy helps you to correct for noise and correct for error. So redundancy is a good thing. So when you compress everything, all the redundancy removed out, then you cannot tolerate noise anymore. Okay? So the compression should also imagine redundancy is a good thing. So a missing letter, you have each letter has a prior probability distribution and requires that many bits of information to know what that letter is. But using redundancy, you can use contextual letters to narrow down what that distribution could be. And if it narrows down so precisely, you can completely fill in, yeah? So you can speak with an accent, you speak with wrong grammar, I still understand you because of the redundancy. I myself speak poor English, and I'm not a native speaker. People understand me because of redundancy in English, yeah? So that's very nice, okay? So therefore, with this conditional probability, you have a conditional entropy which is much less than the original. That's how you can use redundancy to help you. Okay? If the conditional probability given the context letter is 0, then you completely fix that letter just by the context, so you can completely understand the whole sentence. I would like you to invite to dinner. Yeah? So that's the idea. If everybody spoke clearly, redundancy in language will be less necessary. So you can see that across all kinds of languages. You can even go ahead, if I put into a homework, you see how much redundancy is in English versus German versus Chinese. They are more or less the same, because we have designed a very proper language through culture and evolution, which is fit for our ability to decode that redundancy, decode that. And how much redundancy is optimal and things like that, that's a very theoretical, a very meaningful question to ask. So therefore, the redundancy required depends on the noise and tendency for error. Once you know this tendency for error, you need more redundancy. Okay, so therefore, if you have a news anchorman speak clearly, then you have no problem. Okay, so let's formulate it. So this is kind of repeating myself. I'm sorry, let me just. Okay. Your input has the input noise, so this is your original input plus noise. So therefore, your true input you never receive. You only receive a noisy version. And so the original input, you can write this mutual information between the actual input you received and the true ideal input you would like to receive. This is the information you actually like to receive, okay? And of course, if you look at each of them in terms of pixels, then each pixel's mutual information is always more than the whole vector's mutual information due to redundancy. And you want to encode this noisy input by this encoding transform K, okay? And in the encoding process, unfortunately, your physical system, you always have some little bit of noise, the encoding transform, and the intrinsic input noise introduced during the encoding. So let's put a little bit more clear example. A bowfly's compound eye, some eyes, insects have a bowfly compound eye. We just look at one pixel in it. And in this pixel, S is the input contrast. Okay, it's a scalar, so therefore I'm simply written in not a bold form, just S. S prime is the actual signal, including the sample noise received by the receptor. Sampling noise, okay, the actual signal received. And the Ks is a transform that actually takes the S prime and represents it as the response of a large monopolar cell. So O is the response of a large monopolar cell. Okay? So therefore, you just took S prime and represented by a neural filing. That is your encoding. And this K usually is a sigmoid-like function that, so it's like this, okay? S is like this, and Ks is something looking like that. Then you say, can I derive this particular function from the optimization principle? You can ask that question, okay? Another example is retina input encoding. That's in your yesterday's example. So you have n pixels in the picture, and you have n output neurons. Okay, you can even make the output neuron the same n or the less n or more n if you're a bigger n or smaller n. And K is the receptor to ganglion transform. Yesterday in your homework, it's approximated as linear, okay? So you can say each output node is a linear summation of the input nodes with your receptor field form, which is a matrix, plus noise. Yesterday in your homework, I did not do the noise. But today, I can also give you some noise in your homework. You can try to practice, yeah? And so this is a particular encoding transform. And you may then ask yourself, let's say your hardware can only do linear encoding transform. It has to be in this matrix form. Okay? This is your hardware. The only thing it hasn't decided is what is the Kij on each element. And then you say, can I use my objective function to solve for that Kij? Okay? So that's the idea. You can solve for it. Okay? So this is actually n pixels. This is one of the output, OI. And this is the n input, S1, S2, Sn. And this K is the connection from your photoreceptors to one of the ganglion cells. Of course, then you have another regular ganglion cell, another, so all of these retinal ganglion, all these connections has to be optimized simultaneously together. That's what your encoding transform trying to do. Okay? So those are concrete forms. Okay? So encoding is to optimize, find the optimal K such that this is minimized. Okay? So mutual information and neural cost. Okay, so you can imagine it's a battle between increasing information and reducing cost. So imagine if I make my K bigger and bigger and bigger. So imagine it's a linear transform. So the bigger it is, the more negligible this noise is, yeah? So therefore, you can make it bigger and bigger such that this noise is negligible. This term is dominating. Then you really make this mutual information very high because this noise is negligible. You kind of approach the original form here. You can get all the original information there. However, if you make it really big, the output cost is huge because it has to fire lots of spikes. So therefore, you will have to pay more. So nothing is free lunch. You just have to say, is it worth to pay another euro if I get another 2 bytes? You know, if I pay 10 euro, I don't want it. But 2 euro, another byte, so that's good. Okay? So this is the optimization you're trying to achieve. And this is a Lagrange multiplier is your value judgment. You say, I'm willing to pay, how much more am I willing to pay? So this is, you can exchange rate between your cost and benefit. And this may depend on the animal. Let's say a mammal may be willing to pay more, an insect no, it's too small, it doesn't have enough resources, so lambda may be smaller for an insect, yeah?
So in the homework, neural cost can be like time, the running time of the code, like when I was playing with the parameters, if I think if I make k larger, it takes more time to...
No, once you wire it, it's okay. It doesn't take more time, you know. Once the k is already determined, just 1 minute, 1 second, it just passes through.
The computational cost of...
So once the k, you already find the optimal k, this one step going is okay. But the cost is, let's say if your k is too large, then this neuron has to fire a lot. That's the cost.
If we are like writing a code to model this, if neural cost is equal to computational resources.
No, to get the optimal one is not part of the cost. This is done by evolution or done by some automatic algorithm in your brain.
I mean, like if we want to model this, or in our model on the homework yesterday.
Yesterday we did not do the cost. Today we will have a little bit, yeah. Yesterday I just want you to get comfortable with this, so today you can follow the lecture more easily, yeah? So if you did not do the homework yesterday, you may still go back trying to catch up. That means today you will get a bit more tired. But anyway, you arrange your own workload, yeah? So, so this is the idea. And maybe I'm running out of time if I go in, well, how much time do I have? Half an hour. Okay, so maybe I want to skip this because it's only half an hour left. Maybe I want to skip this. I'll give you some other examples, okay? Wow, why do I have so much? I thought I cut down a lot already. Okay, anyway, when there's no noise, you actually want independent component code or factorial code. You probably have heard about these. Decorrelation, redundancy reduction. When there's no noise, you can afford to reduce redundancy. You can afford to decorrelate your output channels when there's very little noise. But a lot of efficient coding formulation does not know what happens if you have a lot of noise. And this is something with mathematical formulation we can do, okay? So in such a case, you actually don't want to reduce redundancy too much because you want to correct errors, yeah? And so in such a situation, you actually want to smooth input to smooth out the noise. Noise can be averaged out and things like that. And I'll show you some concrete examples. So here is one example when the input signal noise is so high you can ignore the noise, okay? So this is, again, in this compound I, we have S as a scalar. You want to encode it by this kind of a sigmoid function. And you want to ask yourself what kind of sigmoid function you want, okay? And you consider there's very little input noise. There only is an encoding noise, which is just at the output you have kind of a quantization step. You can imagine this noise is a quantization step at your output. So therefore, you actually need to maximize the output entropy, okay? The reason is this information, remember, this information is actually equals to the output entropy minus the output entropy given the input, okay? And now, this is completely determined by the entropy of your output noise when the input noise is 0, okay? When the input noise is 0, this is completely determined by the entropy of your hardware. Your hardware has this intrinsic noise. There's nothing you can escape. So this is a constant. So when you want to increase that, you just increase this, maximum this within your cost. Okay, so therefore, this is often you hear about maximum entropy coding. That comes from as a special case of efficient coding in 0 noise. So you already know to make a maximum, you need to make this distribution uniform. Remember, I say if it's uniform, you reach the maximum of 8 bits. If it's not uniform, it will be less, yeah? So what you want to do is make this uniform, but the input distribution is not uniform. So imagine your input distribution is like an input, some input near 0 is more likely, the higher input less. This is a non-uniform distribution. And you want to make the output distribution uniform. What do? You can make this sigmoid function such that, so this is an input to output transform, such that you get your output completely uniform. That's all you do. So therefore, for this more likely input, you want to stretch it into a higher level, higher range of output. For this less likely input range, okay, you stretch into this range. So originally, a very narrow range is stretched out. Originally, a wide range, it did not get so stretched out. That means more likely input range, you want to get more output values to encode it. Yeah? This is in engineering, this is called histogram equalization. In mathematics engineering, this is called maximum entropy coding. And so therefore, to make this non-uniform distribution uniform, mathematically determines to you what should be this. And you can actually solve this by your mathematics. You can exactly find out this is actually cumulative distribution of your original input. Okay? So therefore, KS is solvable like that. Okay.
Is something that you're processing the information you receive and like you're trying to put more weight on.
You're not processing, you're just encoding it. It's like you're encoding Chinese into English, it's like a translator. KS is a translator, like your compression is just encoding it. You're not processing. You can say encoding is processing, yeah. So this is a translation. It's like I'm going to translate my S into O, and this is a mathematical formula to do it. Happen to be solve that optimization equation. Yeah. So yesterday, maybe I kind of trying to say in the beginning is information processing. It is not quite the cognition later, which we will talk about starting on Friday. So this is just still compression. But nevertheless, it's a beautiful theory to say how you could actually do it, yeah? Now imagine suddenly this PS changes, your probability distribution changes, then KS will change. And turns out that's what I mean by when you go from indoors to output, your PS change, your KS change very quickly. So in this case, the change of KS, we do not count it as a cost. Because once I come into this room, my K is fixed. No more cost, it's there. Okay, then I keep on receiving my input, my KS translated into O. And that's it. But if your evolution has already fixed your KS, then you don't have to worry about it. Of course, then this animal is not very adaptive. This animal can only live in this room, cannot go outside because of different probability distribution. Yeah? For animal to be adaptive, they have to have this very plastic brain. They can change. Yeah? And I'll show you some examples of change. Yeah. Anyway, so this is one of the beautiful early examples where a theory completely follows data, not as beautiful maybe as Max Planck's light radiation law, black body radiation law, but it's quite nice. Yeah, 0 parameter, very nice. So when physicists hear 0 parameter, you say, oh, great, just by a theory you get that. Okay, and you can similarly, remember I say in the retina, you have lots of cones distributed. And then you can ask yourself, how should I have 1 million, 10 million cones, how should I put on the retina? The way to put these cones on the retina is a particular K, S. Yeah, S is the light coming in. And you need to translate these light coming in into photoreceptor response. Then you say, oh, I have 10 million, what should I put it? Turns out this can also be solved similarly. You can solve that equation and find, yeah, indeed, it's distributed this way. Okay? This actually involves eye movement and other things given. You have to say the light comes in, could be anywhere, and then you have eye movement, usually put it in your center. Therefore, in the end, the equilibrium distribution is like this. And because the equilibrium distribution of things is like this, then your photoreceptor has to be like that by the equal probability output. Okay, this is, again, a maximum entropy solution. And you can also ask the question of, okay, in hardware, I only have 3 cones, red, green, blue. But let's say my protein can be such that it could be a little bit more red or less red, so therefore you can shift this Gaussian curve any way you want, your protein evolutionary hardware. Yeah? Then you say, but only 3 curves. The only freedom is where you shift it around, yeah, on the horizontal axis. And then you can also formulate it as a, therefore the cone sensitivity is a function f centered around lambda I. So for the red curve, lambda I is lambda red. For the green is lambda green, and so on. So then you say, what should be my lambda I? Lambda 1, lambda 2, lambda 3, such that I can sample my color input in the maximum information manner. And this you can also solve. And I'm not going to dive into details. You can look up as a particular example because I did not make you do this homework. So let's focus on the thing that we do homework, which is a lot of neurobiologists study the neuroreceptive field. And we can try to understand it, yeah? So we remember that input comes in, and it's just transformed by a linear receptive field into an output with some noise. So yeah, for the output neuron I, it's looking like that. And this is the input node J, okay? And this input node could be different space locations, pixel number 1, 2, 3, 4, 5 different locations. Okay, and then this will, K is the receptive field of this neuron, OI. Okay, very good. And so this will make you derive what should be the neuron's spatial receptive field. So for this neuron, you have a spatial receptive field. You have a different neuron, another spatial receptive field. You have n neuron, n spatial receptive field. Okay. But the input can also be time, not space. So different time, Tj. Then what you'll get is the neuron's temporal receptive field. And once I call it temporal receptive field, people don't like this. Then the paper got rejected. So you have to call it temporal response function, impulse response function. But anyway, you need to use the right terminology when you communicate. Or the input can be just 3 nodes, red, green, blue. Okay, so therefore you can apply to color. Then it will tell you what is the neuron's color tuning by K. Okay, or the input can be about which eye. Then it will tell you neuron's ocular dominance property is the V1's neuron's ocular dominance. Some V1 neuron prefer the left eye. Some neuron respond to the right eye. Some neuron respond to as a weighted combination. You can get that. But you can also have combinations of above, for instance, space-time, space-color, anything you want. So therefore, this formulation does not restrict what kind of input it is. It doesn't even have to be visual. It can be sound. It could be touch and all kinds of things. So with this formulation, let's just assume everything is 0 mean. Okay, you can always shift your coordinates to make it 0 mean so that mathematics is slightly easier. We can forget about they are actually distributed not around the mean. You just shift your coordinate to 0 mean. And then you want to find the optimal linear transform to minimize this quantity. So we are going to try to formalize it for Gaussian signals. Again, yeah, this is kind of repeating myself. I'm sorry, because I cut a lot of slides. So. Okay, we need to know the probability distribution of the original input. Again, we need this probability distribution. Now it's non-trivial because it's a joint probability distribution of all of these n pixels. That's really, we don't know. It's multidimensional. In fact, nobody has measured them out. Imagine 1 million pixels, 1 million dimensional space. And what can we do? Then we cannot proceed. And there is we can get a second order correlation matrix. Let's say, imagine the correlation between pixel I and pixel J. So you can have the n by n matrix characterizing all the second order correlation. This is not enough to completely fix this, but sometimes you can have a Gaussian approximation. Okay, Gaussian approximation. Given this correlation matrix, you can have approximation of this original complex distribution by a Gaussian distribution. And the question is this a good approximation? Or just because it's mathematics and easier you use it, or because it's actually a reasonable approximation? And I'm not going to teach about this. You can look at chapter 4 of the book. Turns out that it's actually quite a good approximation of natural visual input. So another thing is that we do not know what this distribution is, but we know its second-order correlation. Then this Gaussian approximation is the maximum entropy version of any distribution. So that means you assume the most unknown about your distribution. So it's a Gaussian distribution given this correlation. Okay, and then, okay, now we have the probability distribution. That's good. And this is the correlation matrix. We can even make an analogous here. So this is the single scalar case, single S scalar case. So the correlation matrix is the variance. Yeah, okay, correlation matrix is the variance. Okay. And with this approximation, then we can get an analytical solution for K. And we also assume the noises are zero mean Gaussian. And because noise is supposed to be independent, so noise here and noise there, the correlation matrix of the noise is diagonal matrix. They are not correlated with each other. They are not correlated with the signal. Okay, then, yeah.
Say if you take vision, for example, images, right?
Yeah.
Then say that this is a good approximation. It's said, I mean, if I take a picture,
Yeah.
then there are regions which are of the same color.
Uh-huh.
So that I know if I know 2 points, then I know exactly the point in between. I know with time. So it looks like high order moments should be relevant.
Yeah. Wait 2 days. I will address that. Yeah. So thank you. Yeah. So higher order moments is actually where the structure is. So therefore, I will dive into that. Okay. Then.
But say, so it's a good approximation because it is a worst case.
So imagine you make another. So imagine you have higher order moments. So that if you write down all the correlation in every order, you can actually write down your whole distribution. Then you can say, what's the difference in the entropy-wise between a Gaussian approximation versus all the higher order thing editing? Of course, we don't know all the higher order. You can just say, let's add the third order first. Just by adding the third order, you find that very little difference in terms of entropy. But it is different in terms of like a kurtosis or these kind of other skewer terms. Yeah. And so I can actually, maybe we can sit down over lunch to look at that, yeah. And turns out these higher orders, you actually need to preserve, don't want to reduce those redundancy in order to recognize the object, and you kind of get it, they are very important. So data compression, you have to remove the second order redundancy and preserve the higher order thing, which actually tells you the object. For instance, a straight line is a very higher order object, yeah. A straight line cannot be taken as all second order, yeah, and that's the thing you actually want to get, yeah. So therefore, with the Gaussian, and then this is the variance, it's a quadratic, it's also Gaussian, it's very easy. Okay, let's recall, let's say if it's a Gaussian distribution for signal and noise, then we already know that mutual information between output and input is like that, yeah? And now this is a very vector form. It's not scalar. What can I do? Well, I'm not going to derive it here. You will find it in the videos and textbook. But you just simply take the variance by the determinant of the output correlation matrix. Okay? So output correlation matrix is your variance if it's just one single scalar, yeah? Determinant. And similarly, the noise variance is becoming the determinant of the output noise correlation matrix. That's it. And so therefore, knowing the Gaussian in a single scalar case, you more or less intuitively can expand it. If you want detailed derivation, it's in my textbook. Yeah? And so therefore, we actually know this formula is exactly like that. Okay, this is the output correlation matrix. Of course, if you know the input correlation matrix, you will get the output correlation matrix. You can just calculate it, yeah? So, yeah. And this is the total output noise, which is the intrinsic noise plus the transformed version of the input noise. Okay, this is the transformed version of the input noise and the intrinsic encoding noise. So yeah, this is the calculation, the output noise. Now, once you know that, you can calculate exactly what is the output noise correlation is. It's actually based on input correlation, so everything. Okay? So therefore, this form includes your transform. So transform is inside this. The transform K is part of this. And transform K is also part of that. Okay? So this is the input correlation matrix and so on. So this is for the signal. This is for the noise. So therefore, yeah, you can, this just linear algebra, you can go through the find this. Okay. And then this is actually the trace of the autocorrelation matrix. Okay? So therefore, once you have the correlation, autocorrelation matrix, you can write down the trace, you can write down determinant, you can run everything. So therefore, the whole thing is written, and the K is hidden in there. The K is here, yeah? So therefore, you solve this equation for the K to minimize it. Then you say, my goodness, so much, but let me break it down for you. I have about 10 minutes or so. So you have this equation, and then let's solve it for a single case. Let's say input is a scalar, output is a scalar. Okay, the matrix is 1 by 1 matrix. Then you write it out. Okay, this K, I'm going to write it just the gain factor G1. Okay, the G1 is a gain 1. So the output is just the gain on the input plus noise. That's it. Okay, plus the encoding noise. This is the input noise. And you write down, this is the probability distribution, and this is also a Gaussian probability distribution. And yeah, then this is exactly that, because this, given the variance, that variance is that. Very good. Okay, and the total noise variance is this. Everything you can derive it. And then you get your, it becomes that. Yeah? So the quantity you have to solve, G, is right there. G1, 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 right there. Very good. And your E now depends only on G1 because your whole K is G1. Okay, only depends on G1. Everything is there. Fantastic. Now you can just solve by derivative. And you solve by derivative, you find it, and this is the solution. And let's just have a look at the solution. And the solution depends only on the input signal to noise. Look, everything else is Lagrangian multiplier, and this is the intrinsic noise. So therefore, it depends on the signal to noise at your input. Okay, and so therefore, I'm going to draw this. This is the scale of the output. So this output actually has an invariance, okay? So the G1 can be positive or negative, so therefore it's a degenerate solution. It can be positive or negative, it doesn't matter. You can flip the sign, this preserve the information, no problem. And this is the signal to noise. So I'm going to make the signal noise really, really high here and very low there. This is just the opposite order, because in engineering, usually you go from high signal to low signal. So you can expand this. For low signal and high signal, it gives you, I'm going to show you that here is the high signal region, and here's it turns out that your G is inversely proportional to your signal power. Okay, you do the Taylor expansion, you'll find out that's the case. And the low signal region, you'll find that it goes the other way. Now let's just understand it intuitively. When the signal to noise is high, noise is negligible, you just simply enhance the weaker signal. Okay? The weaker the signal, you want to give a higher gain. You expand it. Okay, so because weaker signal, this is, I will make it more concrete later. When the signal to noise is low, just sacrifice the weaker signal. Because the weaker signal is corrupted too much by noise. No point trying to send it through. Okay, so therefore, don't send the weak signal. Just focus on the higher signal. So these are two qualitative regions. Okay, and now let's expand to a general case. You have lots of. If they are all independent, you can just parallel do it. But unfortunately, natural visual inputs are not independent, so you cannot parallel do them. Okay, you have to go ahead and solve for this equation with such complicated matrix and solve for a whole matrix derivative. And so what can we do? And again, I leave the derivation to the book, but I give you intuition. You can get this intuition, and you say, that does make sense. I don't even have to look at the derivation because the intuition makes sense. The idea is like this. You have all these input nodes that are not independent. First, do a rotation, which is a kind of a Fourier transform in image space or principal component analysis. That means you do a transfer to make them independent. Now, this have correlation matrix that's not diagonal. You do a matrix transform on this to make this correlation matrix diagonal. That's all. Okay, so that's kind of a rotation. Then treat them as independent because they are not independent, at least in the second order. But since it's Gaussian approximation, second order independent is independent. Then you can solve for each of them independently, in parallel. Except each of them will have different amount of signal to noise. That doesn't matter. You just have the formula. Okay, then after you get that, you can then rotate again. You can do another Fourier transform, whatever, some kind of orthonormal transform again. Because remember, the solution is degenerate. Remember when we look at this, I say the solution is degenerate. It can be G1 or minus G1. That's a degeneracy. And the bigger degeneracy is actually this orthonormal matrix. So it's a degenerate solution space. That's great for engineering, because if you can this solution, that solution, then you say which solution costs less to my wiring power. Then you can find some other costs which you haven't accounted here, which is only firing rate. Yeah, maybe it's engineering you want to, wiring is also your cost. You can reduce it. Okay, which we will talk about tomorrow. Today we will not talk about this. And therefore, the whole thing, you can imagine this is an intuitive way. First of all, you do a principal component analysis to put it into an independent space. Okay, so S original N vector. N vector, you go to N independent component. Then you do gain control on each of these components, G1, G2, G3 in parallel. And then you can just do another orthonormal rotation of this coordinate system. That's your solution. So K is the solution, and this is analytical solution. Yeah, and okay, now let's just conceptually look at it. So it's like originally you want to have the conceptual step. Okay, you have original pixels. You make it into independent components. And then you do gain control on each of these components. You get this output, which is gain-controlled components. And then you do an additional engineering called multiplexing. You do additional mixing of them by an orthonormal transform. And we're going to do it, and again, each of these components will have, some of them is in a higher signal-to-noise region, and some of them will be in a lower signal-to-noise. You just have to apply to all of them in different forms. How much time do I have? Only have 5 minutes to give you a concrete case, okay? So the concrete case, we're going to do stereo vision. Because stereo vision just 2 eyes, 1 eye, 2 eyes, so it's very easy to teach. So not like an n-dimensional, then it's too abstract. So 1 eye, 2 eye, we have 2 images, one to the left eye, one to the right eye. We are going to ignore the fact that each image has n pixels. Pretend we're only looking at just the top right pixel or top left pixel, any just particular pixel there, corresponding pixel, okay? And so therefore, it's 2-dimensional. I'm not going to have a 2n dimensional, okay? It's 2-dimensional, just 2-dimensional. And in our eyes, we have the input comes into the 2 eye, left eye and right eye, and they go through this and then go to V1. And V1 is where the 2 eyes combine. So we want to know how to combine these 2 eyes is a good way. And this combining 2 eye is my K I want to solve, okay? And so therefore, this is like combining 2 eye to a V1 neuron. That's the K we want to solve, to optimize, okay? And the solution, I don't know whether it will be the right solution, but experimental data has already shown us what should it be. This is if you stretch out the V1 cortex and lay out in a flat surface, you find, this is called ocular dominance columns. They just basically visualize the neurons tuned to the left or right eye by black and white pixels, okay? So a neuron in the black location is a neuron tuned to the right eye, neuron in the white is to the left eye, so they kind of different neurons cluster into neuron preferring the left eye input is clustered together, and neuron to the right eye input clustered together. This is called ocular dominance columns. Experimental data we can compare the theory with. Okay, so the idea is at input level you have n equal to 2 because there's only 2 eyes. Okay, so the input is a 2-dimensional vector, 2 eyes. I forget about the, so therefore imagine this is a pixel 1, this is pixel 2 at the same location in 2 eyes. And it has input noise, 2-dimensional vector. And you want to have this encoding K, the matrix is a 2x2 matrix giving to O1 and O2. That's what you want. And so the matrix is 2x2 matrix. And that will give you output like that with the encoding noise. And so, for example, your particular output O1, let's say this particular output O1 is by K1 to the L. This is the left eye. L means the left eye, R means the right eye. And K1 to the right eye, so this connection and that connection that you want to solve. Okay, the two connections you want to optimize to solve. Okay, and then you can calculate the input correlation matrix between the two input. That's just 2x2 matrix with diagonal element, which is the input variance in the left eye, input variance to the right eye, and off-diagonal elements, just the correlation between the left and right eye pixels. Yeah, and usually it's symmetric unless some people have these amblyopia, the 2 eye will have a dominant eye, and so on. And so you're symmetric normalized by the turnout set. Okay. Now let's go to the second stage. You need to do this principal component. So you take the original input, S1 and S2, and you solve with this correlation matrix. You want to go to 2, 1. That's correlation matrix with no off-diagonal correlation. That's the idea. And you can solve for it. You find one is the summation of the 2 eyes. Okay, this S plus is SL plus SR, and S minus is SL minus SI. This exactly has 0 correlation. Yeah, and so this is the 2x2 matrix is easy to diagonalize, especially it's symmetric. We are comfortable with symmetric matrix. Yeah, and the diagonal is not there. Okay, so this step is called decorrelation. Okay, so this first matrix KO, it decorrelates, it goes into that. Then you can see, I can try to visualize, okay, left eye and right eye input are correlated. So therefore, if you take some pixel there, then these 2 pixels are very bright, so that maybe that dot, okay? And these 2 pixels are very dark. And this is the correlation, yeah? And then you can see this correlation matrix, I want to diagonalize the 2 eigenvectors. One eigenvector is along this one, and the other eigenvector along that one. Now you see that this and that, they are not correlated, right? Visually, you can see this new 2. So this transformation is a 45-degree rotation in a 2-dimensional space. That's what orthonormal matrices are. Orthonormal transformation is always a coordinate rotation. Okay? So this 45-degree rotation, it gets you 2 new axes, which I call it S plus and S minus, S plus and S minus, and they are no longer correlated because what value it is on the horizontal axis has no correlation with the value is on the vertical. On this axis, S plus, S minus are no longer correlated. Yeah? Okay? You get that? And then the next step, we do the next step, you say, oh, now I need to have the gain control. What the gain control depends on the signal to noise. You can see that this has higher signal. Why? Because the 2 eyes are redundant, they are correlated. So if you add them together, the signal is even stronger. Yeah? And so this does have higher signal. See, signal is 1 plus R. And this have a weaker signal is 1 minus I. So you can say one is a high signal, one is a low signal. And therefore, you plug these signal in, you will get G, okay, for the gain, G plus and G minus. You plug it in. And once you plug it in, you get a G plus and G minus. G plus for the plus channel and G minus for the G minus channel. There's summation channel and difference channel. And what is this? The physics in this is ocular contrast. You want to get a contrast between the 2 eyes. And this is the average between the 2 eyes, it's cyclopean. Okay, you say, you will go to a movie theater, usually it's just one picture. The 2 eyes see the same thing. You can still know the story, everything very well. So what's the point of the difference between the 2 eyes? Why do we want a difference between two eyes? This is when you want stereo vision, when you want 3D. Yeah? So you need it. But what if you say this signal is too poor? Then abandon it. But if the signal is good, keep it, then you can get 3D. That's how I see it in 3D, even though it's 2D, two images. Okay? So therefore, the 45-degree rotation, then the gain control, the gain, if the gain is high, you keep the channel. If the gain is low, you throw away the channel. Yeah? That's how the V1 is trying to do. So this gain, you can imagine, okay, so I'm going to go through adaptation. So when the signal noise is high, you want the gain such that you give more gain. So originally, this is like the summation channel and difference channel. Summation channel has very big signal variation. Difference channel is weak signal variation. You want to expand by this gain very high so that this really expanded. You're trying to amplify that channel. Yeah? Does that make sense? So originally, this channel has such a small, originally this channel has a small ellipsoidal distribution. Originally has an ellipsoidal distribution with large signal here, weak signal here. Now you make a spherical distribution, large signal here and large signal here. You want to expand this difference channel, okay, in order to get a 3D information. That's what you get, okay? Enhance the contrast channel by a stronger gain to it. But if the signal to noise is too weak, then you say, well, this is mostly noise. I don't really need it anymore, okay? Original signal is like that. The noise is dominating. So you abandon that. Then you do not have this. You even make this to 0. So when you, and in the dark, you have very difficulty seeing stereo depths. You will have perspective depth. The reason is this G minus is 0, okay? So you see something as closer or further by its size. It's something very big, it must be close, something very far. It's also by perspective cue. You no longer use the difference between the two eyes trying to calculate the depth, okay? And this is actually one of those things that you will find. And so that's an adaptation. Okay, this, as I say, for this region, you are in the high signal-to-noise region. You want to amplify the weaker signal, which is your ocular summation. And here is the low signal-to-noise region. You want to throw away your ocular, weaker signal ocular difference. Yeah, ocular difference between the eyes. But here, when it's nighttime, you want to throw away this difference between the eyes, which is in this low signal-to-noise region. Okay, then you multiplex. Why do you want to multiplex? Which it will actually make more sense in spatial coding. So I'm going to maybe skip that because we don't have time, yeah? How much more time? 1 more minute?
Probably.
And probably 1 more minute, okay. So let me show you, this is, in the end, I said we want to have a theory with experimental test. So we actually are going to have an experimental test. Well, actually, brighter, dimmer environment, I already showed you. You can have different animals with 2 eyes very far away, 2 eyes very far away. They have little correlation between 2 eyes. 2 are very close with high correlation between. They will have different solutions. And you indeed will find the different solutions. You will have some people, even have like a disease with strabismus. They will have, then their brain is different from our brain because they're strabismus and so on. And yeah, I'm too good. Okay, the experimental test is this. Okay. So because you have a summation channel and difference channel, and the gain to it, if there's no noise, then this should have, the gain, okay, signal to noise, by the correlation, you have the signal power in the 2 channels by this formula, and the gain goes like that. Okay, the gain to the summation channel, gain to the difference channel have this ratio, completely determined by the correlation between the 2 eyes. Okay? So here's the experiment test. What if we change correlation between the 2 eyes? Then you should change the ratio between the gain. Can you measure it? The best thing is go to the neuron and measure that's the case. But in a laboratory that doesn't have biological access, you have to measure in humans without opening up their brain. So how do we do that? We do it like this. Prediction is if you make the input like this, if you add these 2 together, it gives you perception A. Subtraction together give you perception B. Then you ask people, do you see A or do you see B? They have to tell you. Okay? So they are more likely to see A if the G plus is high they are more likely to see B if the G minus is high. Does that make sense? Okay? So you ask them, so let me show you an example. Imagine the input to the left eye is a cosine wave in space and time. Input to the right eye is also cosine wave in space and time, but it's 90 degrees apart from this. You can add them together, get a drifting wave, motion wave. Okay, this is drifting up and down differently. This is also in the video in the course. But anyway, you ask people, is this drifting up or drifting down? They just have to answer you, drifting up or drifting down. Okay? And I'm trying to see whether they answer this way or that way, trying to get a hint of G plus and G minus. And G plus and G minus, we make people change it by giving them different R's. We make them look at the same image so the R is equal to 1. They make the R equal to 1. Okay, they just give them same images. They keep on making them showing the same image. Or make them see opposite images. Okay, this is a photo negative of that one. Then R is equal to minus 1. Or you can make R equal to 0 by showing them independent images. Okay? And so this is how we manipulate the people, and then we find they look at this more, or they see this more versus that more. Change. You only need to very short adaptation to make that happen. And that's a particular prediction, and that's experimentally confirmed. So that's it. I already took too much time. But anyway, this is a tour de force, and then you can slowly digest through the homework with another homework. Tara will give it to you. Or you can just watch the video, or if you have time, do both. Okay. Thank you very much.